I will teach you about heaps. Heaps are an implementation of priority queue, which allow you to repeatedly remove the largest or the smallest element over and over again in guaranteed log n time. But if you want to remove something from a tree, that's either the largest or the smallest, you can do that using a binary search tree. And that could work, but binary search trees aren't guaranteed to be balanced, so it could take longer than log n time. So which is why we use a heap. A heap is shaped like a binary tree, actually, but it's different. It has a property called the heap property. And okay, let's say there's two types of heaps right now. There's max heaps and min heaps. And let's say we're talking about a max heap. In a max heap, the heap property is that the parent is always greater than the children. So if you apply this property to every node in the tree, then you end up having the largest node at the root. And this is how it looks like. Here's an example of a max heap. Okay, so you can see that for all the nodes, the parent is greater than the children. Right? Max heap. And this is how it's implemented. It's represented as an array. Like this. 10, 5, 7, 1, 3. And when you insert into this max heap, you insert at the next available element in the array, which is here. And this would correspond to this location here. Right? And since this is a max heap, this item here has to be less than 7. So if you insert, let's say, 6, goes here, that's fine, right? It goes here. And the next available element is here. But let's say you insert something like 11. Then this could violate the heap property. So then what we do is we reheapify, which is when you swap the children and the parent, like that. So then this becomes 11, this becomes 7. But since 11 is still greater than 10, which still violates the heap property, we have to reheapify again, like that. And then this becomes 11, this becomes 10. Right? So then every time you insert something, you may have to reheapify a couple times. And since the height of the tree is log n, and the maximum number of times you have to reheapify is in the worst case where the new element is greater than the root. So the most number of reheapifications you have to do is log n, which is why adding to a max heap is guaranteed to be log n. And removing is also pretty easy because the largest element is always at the root, right? So then when you remove, you swap it with the most recent element. 7, 11. And then you remove from the tree. Right? And then you reheapify down to the base. So since this is max heap, we want the greater element to be at the top, right? So instead we have 5 and 10, right? But since 10 is greater than 5, we reheapify this way. So then we swap 10 and 7. And then the heap property is satisfied again. Right? And for a min heap, it's the same thing, except the heap property is that the parent is always less than the children. So then you end up with the smallest element at the root. And you can do the same thing and achieve the same log n time. And this is why heaps are useful.